Hello, my name is Michał Zawalski and I'm excited to share with you Adaptive Subgoal Search. It's a planning algorithm that learns to decompose a given problem into smaller subtasks, making it easier to solve. In this presentation, I will discuss the approach and its benefits. This is a joint work of Michał Zawalski, Michał Tyrolski, Konrad Czechowski, Tomasz Odrzykuść, Damian Stachura, Piotr Pienkos, Juch Łajwu, Łukasz Kuciński, and Piotr Miłoś. Our goal is to solve problems that require advanced reasoning. So to verify the potential of our algorithm, we tested it on proving inequalities and two classic puzzles, Sokoban and Rubik's Cube. These are tasks that represent a range of problem-solving challenges. When facing a complex task, a naive approach is to use a graph search algorithm like BFS. While this may work for small problems, it becomes computationally infeasible as the problem scales in difficulty. To overcome this challenge, heuristics become essential for effective planning, such as MCTS, Best First Search, or A*. We use a different approach to this challenge based on Subgoal Search. Rather than building a tree of atomic actions, we search the state space using subgoals, high-level objectives that can be achieved with a few actions. For example, in the Sokoban puzzle, a subgoal could be to push a specific box onto a target, or for example, to reach the far edge of the board with the agent. By using subgoals, we can advance the search more quickly, making the planning process more efficient. Also, we want our subgoals to adapt to the problem structure and take into account the local complexity. Why do we need that? Imagine driving a car. When you approach a crowded crossing, you need to plan your moves carefully, paying attention to every vehicle, every pedestrian, every turn. However, when you enter an empty straight road, you can simply focus on reaching its far end. You don't have to be careful. And similarly, challenging tasks typically have difficult parts, bottlenecks that require careful planning, and easy parts that we can easily skip with longer subgoals. We want our method to recognize these patterns and take advantage of them. To build a search tree, we use the following components: subgoal generators that propose sets of subgoals, policy that determines the low-level path that connects subgoals, and a value function that estimates the distance to the solution. Each of these components is trained on offline trajectories. We use only supervised objectives based on this data, which makes the training stable. To build a search tree, we iteratively expand nodes with generators. The order in which nodes are expanded is determined by the planner. So how do we achieve adaptivity? There are a few natural ways to implement it, but not all work equally well. We use a set of subgoal generators that propose high-level steps at different distances. Each generator is trained to output subgoals that are suitable for a particular distance. They range from short-term goals that use the benefits of search to long-term, optimistic objectives that advance faster. In every iteration, the planner decides which generator to use. This way, it can control the planning horizon based on the progress of the search. We tested several strategies for scheduling subgoal distances. One that worked best was to strongly prioritize the longest subgoals and retract to the shorter ones only when the search is stuck. This approach outperformed other, arguably more natural approaches by a wide margin. Importantly, we found that every adaptive method we tested outperformed the non-adaptive subgoal search. Another approach that we considered for achieving adaptivity was to use a single generator that decides the distance of each subgoal it generates based on the state it is given. However, we found that this approach didn't work well in practice. A detailed discussion and results of all our approaches to implementing adaptivity can be found in the paper. Moving on to our results. Adaptive subgoal search outperforms baselines across a range of problem instances. Specifically, our approach achieved success rates of 93% in Sokoban, 99% in Rubik's Cube, and 96% in int. In addition, we set new state-of-the-art results on the hardest problem, int, which involves proving inequalities. In comparison, the non-adaptive variant, K-sub-S, is less successful, failing to solve twice as many cases as adaptive subgoal search. Additionally, our method typically required a computational budget that was about 3 times smaller than K-sub-S. Another key finding of our work is the resilience of adaptive subgoal search to various types of domain shifts. For instance, in the int environment, we evaluated models trained on proofs of length 15. As we can see in the figure, our algorithm can deal even with twice longer proofs than it was ever trained for, while its non-adaptive counterpart fails. In fact, we are surprised to find that our mechanism of adaptivity also leads to improved performance in out-of-distribution generalization, even though this was not a specific goal of our work. We conducted similar analysis for the other domains, and the results are presented in our paper. What are the properties of adaptive subgoal search that make it successful? The key idea behind this algorithm is that it decomposes complex problems into easier parts that can be solved one by one. The adaptivity mechanism makes it resilient, both to the local complexity of the task and to the challenges not encountered in the training distribution. Because the planning is guided both by the value function and the subgoal generators, the mistakes made by one of them could be mitigated by the other. And lastly, our algorithm benefits from stable trainings since we transform offline trajectories into fixed training samples for our components. Still, there are ways to further improve adaptive subgoal search. We want to improve this search by learning latent representation of states and perform planning without access to the environment. We are also working on handling stochastic domains. We can optimize the length of the solution or maximize the rewards. Finally, we expect adaptive subgoal search to be applicable in other domains like robotics to teach robots to solve complex tasks using just offline data. To sum up, in our work we introduce adaptive subgoal search, a planning algorithm that successfully solves complex problems by decomposing them into smaller subtasks, high-level steps. The adaptivity mechanism makes it efficient and, moreover, robust to distribution shifts. Thank you very much for listening. If you have any questions, we are happy to chat with you.